Hello everyone. We are restarting our Turbulence seminar online, and we are very happy to have Professor Bhattacharjee, J.K. Bhattacharjee, as a speaker in the opening seminar. JKB does not need any introduction. Everybody, well, JKB in short. So now in IIT Kanpur we call by this initials. So he is known to everyone, I think, in the audience. But just to do my formalities, I will just say a few words. He did his PhD from University of Maryland, where I too went for doing PhD. Then he came back. He did postdoc in Santa Barbara. Then he came to IIT Kanpur, and he was here for 10 years. I had only small overlap, and then he moved to IACS, then to St. Bose. After that, he became a director of HRI. And after his directorship, he's back to IACS as a distinguished professor. And he's an excellent teacher. I think we have seen him giving lectures, and excellent researcher in turbulence, nonlinear dynamics, non-equilibrium statistics. With no further ado, I will just request JKB to start his lecture.
All right. Thanks, Mahendra. And this hopefully, I mean, is going to be of all specialists that I'm talking to. But hopefully it is not going to be a rehash of old things. So, and the talk is designed for Mahendra and his group, so it should work out all right in that sense. So, all right. So what I'm going to talk about is a stratified fluid and turbulence in a stratified fluid. Stratified fluids are common, and isotropic fluids are easier. So one hears a lot about Kolmogorov, but unfortunately hears very little about Bolgiano-Obukhov. It is something I personally learned from Mahendra, and so all right. So here we are. So to get things started without any really introduction, so there is this turbulent flow which involves vortices and so on and so forth, and it's extremely complicated and so on and so forth. So what one wants to do is extract some easy features of it. So this whole talk will essentially be about extracting some features of a turbulent flow which are easy for, let's say, doing calculations. So, and fortunately, because of Kolmogorov, it has also become very relevant. So this is the great benefit, that you pick out something where you can at least do some calculations, and Kolmogorov gives it sanctity. So one starts with the total kinetic energy of the fluid. So the turbulence means there is randomness. So there is averaging. We talk about averages, and that's exactly what we are doing over here. There it is the average of the velocity square, and then a few just writing, going from coordinate space to momentum Fourier space, and writing in terms of the correlation function. That's the correlation function. D3k is the k squared dk, and this is written as ek times dk, and the ek defines the so-called energy spectrum. So we have a correlator, which is this, and you have a energy spectrum, which is the correlator times k to the power d minus 1 in d dimensions. Here it is d equal to 3, so you are looking at d equal to 2 over. So if I look at this energy and don't have any dissipation or forcing, the energy is going to be a conserved quantity. And so one is going to talk about a Kolmogorov spectrum. And when do I see the Kolmogorov spectrum? It is when there is a steady state. So, all right, so let's go back, start with the Navier-Stokes equation. And that's what you see over here. And you have the usual terms, the acceleration on the left-hand side, the partial derivative here and the convective derivative here, and what it is forced by, sorry, what happened here? Should be going back a step. Yeah, that's what I want to look for. Yeah, and where am I? I'm going back. Here we are. So so there is forcing coming from there is a pressure gradient causing a force, there is the viscous dissipation, and there is a stirring, which is, if you always imagine that turbulence in a teacup is what one is thinking of, and stirring your coffee, so you are doing some stirring at large lengths. So that is what that F alpha is all about. Incompressible flow, so that's the divergence condition over here. And then you just look at the energy equation. The nonlinear term that you see and the pressure gets related to the nonlinear term through the divergence free condition, and the energy equation thereafter works out as the time derivative is equal to, so the time derivative here has a right-hand side, which is a dissipation, and the right-hand, another term, which is the forcing. So steady state means that the two dissipations and the forcing cancel out, and you have a steady, the total energy is a conserved quantity, and the what essentially you can call it a sort of mean field theory. If there is a density gradient, there is going to be a change. So now we come into the homogeneous, the inhomogeneous fluid, where you have a gradient in the density, and let's say we are imagining that the density is caused by a thermal gradient. The thermal gradient across a height d is delta T over d, and you have to bring in a buoyancy force as a result. So the buoyancy force is in the z direction, which you see over here. This delta A3, alpha 3, sitting over here is and you are working in a Boussinesq approximation, which is essentially saying that after you have made some relaxation in the density being constant to include the buoyancy, you have thereafter you are back to an incompressible fluid where you can write a del alpha u alpha. So you have basically you have this buoyancy force, but you don't have any sound wave in the system. So that's what the Boussinesq approximation is all about. I've put in the buoyancy term, which means I have taken a density variation into account, but that only because of the temperature difference, and I have put back the incompressibility condition after I have done that little bit of jugglery. So, well, here is the change set of equations, the equations which will be concerned with for most of the talk, that there is Navier-Stokes with an additional forcing there, and there is the heat diffusion equation, which for good measure, I have put in random forcing in the heat diffusion as well, that you imagine. Now, how you do this in an experiment, I don't know, but obviously if you are doing it in a numerics, it is possible. But sometimes the experimental results are such that it seems there is a built-in thermal. So anyway, that said, this is the starting point. Yeah, go ahead.
In the previous slide.
Yeah.
So this U3 by D term in the temperature equation.
Pardon?
In
the temperature equation, what?
This U3 divided by D, what is this?
Oh, that's the, I mean, you put in the density gradient, so the total temperature field has, when you put, this is only the temperature fluctuation. It's the delta T, you see.
So theta is delta T.
Theta is delta T and not the total temperature. The total temperature is has the delta T in addition. It is this total temperature is to be written as T plus some mean T plus the delta T, and out of that delta, the fluctuation over here has gone into the theta, whereas this whole thing would have been T, which is the total temperature plus the thing, and the total temperature is that has the remnant, which is this U3 over D. It is the U3 coming from here, and there is this derivative which is in the Z direction, so that brings in the U3 over D.
So it's basically the U dot grad of the background temperature, essentially. Right?
Yeah. But vital for energy balance. I mean, because the energy balance will be written in terms of the, you want it in terms of the temperature fluctuation. And so when you do it in temperature fluctuation, you get the cancellation, which normally, see, there is a part of this buoyancy term here is going to put in energy to the system. When you take a scalar product with U, you pick up a contribution from over here, which is U3 times theta. And this is exactly the term which cancels that out. And so when you write the energy conservation, so you have energy conservation as the velocity, which is a random field, plus the temperature, which is the fluctuation in the temperature, and it is the random variable rather than the pure temperature with which one has to start out the diffusion equation. So the E defined, so the energy now has a kinetic energy which one talked about before, and in addition what one could call a potential energy. And if you take the derivative, you have the usual dissipative term, which you see over here, augmented by the theta, and then the forcing term having two terms over here because I put in a. If the fluid is stably stratified, which is what I have assumed with the signs till now, everything works out all right. That is, I can balance, I can have a steady state by balancing this against this. And I can talk about thereafter the constant energy, where so there would be energy flowing in and energy being dissipated, energy being stirred in, energy being dissipated, keeping the whole business conserved. So all the good things which were happening in the isotropic case can still happen over here when it's stable. But if it is convective, then you have a problem, because if you write down the same thing, the E would come with a negative sign over here. So there would be a negative sign over here, there would be a sign flip over here, and the conserved quantity would begin to look a little problematic. Well, now what one is going to say, would it still hold for convective turbulence? Maybe in some limiting situations when the E still remains, in spite of this negative term over here, E remains positive, and the negative sign over here is forgettable for a large Prandtl number. So maybe large Prandtl number limits and are a good thing where it works. But that's a more tricky issue, which Mahendra has written a lot about. And we will, in general, until the last slide, I'll stay away from it.
I had a clarification, JK.
Yeah,
so,
sure.
So mathematically, the equations are still valid. The equation that you've written is still valid, even if the temperature term has a negative sign. That is, if it's convectively unstable, right?
Yeah.
So mathematically, the second equation is still correct. It's
yes, right, but also with a negative term in front of the lambda.
Right. But you're saying that this is a more subtle case because the interpretation is sort of...
The interpretation is a bit problematic.
Okay.
Because the energy need not be, I mean, you would like a positive definite energy, and because when I'm talking about something being fed, as I will in a minute, some energy being forced in at large distances and being dissipated at short distances, I have a positive quantity in mind. I mean, this direction of flow could become a sort of troubling issue.
Okay.
That is what I'm after.
Okay, thanks.
That is, if I have let's say, if this term over here, I pick up a negative sign in this corresponding equation, and that becomes and if that dominates, then I have an energy being pumped in at large wave numbers. So that is something which would be a bit iffy. So that I mean, that is the kind of situation I am trying to avoid. That it is all energy being dissipated at large wave numbers and being pumped in at small wave numbers. So to keep that picture, I'm saying that eta large would keep me there, and if the Ri times theta square doesn't become too large, then I wouldn't be upsetting things too much. But whether one survives even without that is something I'm not confident about making any statements there. That's what I'm saying.
Okay, thanks.
But yeah, so all right. Now comes a new possibility, that when I start looking at this derivative, I have all right. Let me go to the next slide, I think, before so all right. It's a question of talking about the spectrum, which is the issue of that's what Kolmogorov essentially did. That he talked about the spectrum of this kinetic energy, which is defined in this manner, and it is E of k, energy spectrum, whose E of k. And what this was Kolmogorov for the pure fluid, and he had this picture that The dissipation, which is like wave vector square, takes place at very short distances. The forcing is almost is natural to have at large distances, so which is small k, and therefore the conservation law which we had in the total energy sort of tells you that there is going to be energy driven into the system at large spatial scales, dissipated at small scales, and therefore there would have to be a transfer of energy continuously across any intermediate scale which you look at, focus your attention on. You will be find energy being transferred across that in order that the total energy can have a conservation law with the forcing and the dissipation going on. So the total energy, so what is this rate at which you are transferring energy? You look at the energy which is contained between the from a wave number which is very small to a wave number k. This wave number k now is neither too small nor too big. So you are sitting somewhere in the middle where there is no effect of forcing, not much effect of dissipation, and this what one calls an inertial range, and this k happens to be in the inertial range. The zero is another name for something which is at, let's say, at the end of the inertial range, and this is essentially what you are seeing over here. This E of k is the total amount of energy which is sitting between the large length scales and a wave number k. So this is, and now you want to know at what rate is this energy changing. So this energy changes according to, so just take a derivative. So you take a derivative and call it, so it's some epsilon k, and you will be picking up, you see only one term over here. There is another term which is the complex conjugate. So so imagine that it is there. So it is, you take a derivative, and that is what, so that is the rate at which your energy between 0 and k is changing. But the total energy is conserved. So where is it gone? It is gone to scales which are greater than k. So epsilon, small epsilon there is the rate at which your energy is flowing from scales below k to scales above k. So this is what Kolmogorov assumed was going to be independent of scale, and therefore the point that this E of k which you see over here is going to be determined by the k, obviously, and by epsilon, because obviously if you put in a more energy, the E of k has to be bigger, and if it is lower, it has to be smaller. So it's determined by epsilon, the amount of energy flowing. It's determined by k. You do a dimensional analysis and you get so now you are looking at a different situation slightly, because the total energy is given by a sum of these two terms. The spectrum, though, is by sort of convention always the kinetic energy spectrum. So the kinetic energy spectrum is what you are going to be looking at. The flux, however, the epsilon k certainly has two terms in it. Epsilon k has a part which is the velocity part, and the other which is the thermal part. Now this so-called Bolgiano limit is that you assume that at sufficiently large Richardson number, Now, this large Richardson number, small Richardson number is another bit of a problematic nomenclature, which I'll focus on a minute later. But the point is that just assume that if I have a large enough Richardson number, then the second term over here is going to be accentuated, and epsilon, there can be a situation where epsilon k is dominated by that. And now you drop the you say epsilon k is all theta. The energy spectrum is obviously by definition the kinetic energy spectrum, and it is to be determined by the flux, which is the temperature. So now you do a dimensional analysis once again, and the dimensional analysis yields instead of a k to the power minus 5/3, you come up with a minus 11/5. All right, so that's Bolgiano-Obukhov, and the k to the power minus 11/5 is a spectrum that you expect to see for the from what I have said, for a stably stratified fluid. In its, mind you, there is no, it is just saying that it is there is a isotropy assumed over here. This isotropy is obviously, isotropy is not there in this problem. So the point is that this B0 that you are looking at, that B0 is, it's a possibility that it depends on the angle at which you are looking at things, and the B0 is what one is talking about over here, is just an angle average number. But if one looks at the innards of the thing, the B0 might still, well, the dimensional analysis simply gives you what the dimension of K has to be to match things, but does not, if there is a theta dependence on the coefficient B0, it does not give you any indication of that. So, well, all right, this is the point is that where is the 11/5? Do I see the 11/5? And here is the thing which had essentially started, really drawn my attention to it. This is a page from Kumar et al., Mahendra's student who was in England. I'm not sure now where he is. But this is one of the very few numerical simulations that exists that has seen evidence of clear. So what is being done? You measure E of k numerically, you multiply it by k to the power 5/3 and try to see whether it is flat or not, and then you multiply by k to the power 11/5 and check whether it is flat or not. And this is where, it is very, you have to focus on this picture over here. The first picture to the left, and look at this region. That is where the compensated spectrum that is multiplied by 11/5 is reasonably straight. If you, on the other hand, if you were to multiply it by 5/3, then which is done in the next slide, then it is not so straight. And this is as the caption which you can't read is at Richardson number of 0.01. Now, this is what I said. I was talking about Richardson number of high Richardson number. Here is Richardson number 0.01 and seeing Bolgiano. No conflict here really, because this Richardson number is a funny thing. When one looks at the Richardson number, you get the expansion coefficient times delta t times g in the numerator. But to make things dimensionless, you have a velocity square in the denominator. And this velocity square, depending on what your choice of velocity square is, this Richardson number, where the driver is the delta t, the Richardson number can look like 0.01, but its effect can be much greater than that. So that's something which one has to keep in mind, that these Richardson numbers being 0.01 and 1, there is a bit of, it is, the buoyancy force is dominant over here. That is the basic point. It is the next picture which really got me started. This is the same, the numerics done at Richardson number of 0.49. So that is 50 times bigger Richardson number than you had before. And you would expect, you would see a much larger span of Bolgiano-Obukhov. And that, as Mahendra pointed out in a later paper, does not happen. It is the 0.01 which is the much better advertisement for the Bolgiano spectrum. And that really is the inspiration, for whatever I'm going to talk about now. So, all right, before I go into that, this question of anisotropy and so on and so forth, one needs to, here is this question of trying to make it dimensionless. The question of dimensionless, d is standard, this scale distances by d, that is the height of this, atmosphere, or the height of the fluid layer, and time by this d square over nu, which is again something pretty standard, but the velocity is scaled by a RMS velocity. What I need really is a velocity which would be relevant for the Reynolds number. So if I assume that this u is relevant for Reynolds number and then do go ahead, then what you find is that you have a Reynolds number sitting here and over here, and you have, this is the Brunt-Väisälä frequency and omega squared, and the Reynolds number sitting in the denominator over there. We are in the Boussinesq approximation, so I take and then just focus on the last line over here, that there is this driver temperature on the right hand side is this, and look at the third component. When it's the third component, that is in the z direction, you have 1 over here, and essentially you have a del x square plus del y square at the top, and grad square in the bottom. So what you want for the fluid to be being Bolgiano-like is that this term has to be sizable. I mean, you don't want the non-linearity which comes with this Reynolds number over here to be the dominant player in the game. So you want this to be subdominant and this to play an important role. So it is omega square over r Reynolds number, which needs to be pretty big. But you don't want it to be very big either. And that is the other problem over here, that if this becomes very big, then you are essentially freezing out the third component. So the U3 is frozen out. If this is very big, then the theta, this other part over here, this has to vanish, and that fixes the theta, and the U3 is out of reckoning. It does not couple to the other velocities anymore. So you have more or less a two-dimensional problem, and you are very large, what I'm after, very large Richardson numbers have their problem. So you can't go very far over there, and one has to be careful. So, all right. So now the question is that...
Good question.
Sure, yeah.
So, at high Richardson numbers, the eddies, rather than being isotropic, become very horizontally flattened.
Yeah.
Right? But it's not quite 2D turbulence in the sense of the standard 2D turbulence.
No, it is not standard 2D. It is Kolmogorov-like once again.
Right.
Yeah, the spectrum is more, and there is no entropy cascade. No.
Right. Okay.
Yeah. Absolutely.
Yeah.
So it is a 2D Kolmogorov essentially, and not a 2D, real 2D. Yeah, absolutely. Should have said that. So now my idea that I mean, I have to go from Kolmogorov. So I'm assuming I'm in a Richardson number range where I should be seeing Bolgiano. Obviously, if the Richardson number is very small, then I should be seeing Kolmogorov. And if I increase the Richardson number, I should see more or less Bolgiano. Now, how do I handle? I mean, I have to get an expression for the energy spectrum crossing over from one limit to the other, an expression for the energy spectrum. And now the thing is that it is the kinetic energy always, and often I don't see the kinetic energy being expressible as a sum of, I mean, it's just the kinetic energy. I don't know what to really do with it, but I know what to do with the energy flux, because that is the derivative, and that is the derivative of the energy. The total energy is u squared plus theta squared, and here is the derivative, which looks like this, and there is a Richardson number sitting over here. If Richardson number is very, very small, the epsilon k is kinetic energy dominated, and if the Bolgiano limit, as we talked about, Richardson number is very big, then it's Bolgiano. So how do I, and the question is, how do I, how do I put this in a maths? And so if I want to put this in a maths, I have to put the spectrum on the right-hand side. The epsilon k is epsilon k, and that's which will become just k independent in the inertial range epsilon. But it's the right-hand side where I want to see the energy spectrum coming. And here is where some 70-year-old wisdom comes in, that if you want to get started, this is what you can do. So you look at the dissipation range. So I look at this chap and the dissipation range over here. So the dissipation range for u dot, and if I look at it in the dissipation range, then it is just the viscosity times p squared. Viscosity u dot is p squared nu u, and so you have this, and what you have is a correlation function. So you have a correlation function, and what we learned from the first slide is that correlation function times p square is the energy spectrum. And so what this term is that it is the energy spectrum times p square dp. But this is in the dissipation range. How do I carry it over to the inertial range? And this is where comes in Heisenberg's 70-year-old work, more than 70, that put the energy transfer in the inertial range in a similar form, but change the viscosity to an effective viscosity, which you are going to generate out of the energy spectrum and the wave number. So you do a dimensional analysis, and you find that the answer, dimensional analysis in terms of E and P, gives you this. But now the energy transfer, at what scale do you need it? You need it at all scales greater than K, because the energy is being transferred to all scales from K, scales less than K, to all scales greater than K. And so you put in a sum over all those, and this is where you get the expression for nu effective. And now you are in business. You want to write the inertial range kinetic energy transfer, and the inertial range kinetic energy transfer is consequently given by this. You have a viscosity, and so this is all Heisenberg 48 or 49, whenever that paper was written. But now comes I need a similar expression for the potential energy, the epsilon theta. So this is the epsilon kinetic energy. I need a epsilon theta, and then I play the same Heisenberg game. I play the same Heisenberg game and find that instead of this chap, I get the same analysis gives me this, and the effective thermal diffusivity looks like that. There is a Ri in tagging it, and so I have the total energy inertial range energy transfer written a la Heisenberg in the form which is this. So that I take as if I want to look at a crossover in a situation where a kinetic energy flux is to be changed to at large Richardson number to a Bolgiano theta flux, then I start over here, and now it's a question of what are you going to do? Well, you do a couple of definitions first, and now I have to impose the inertial range constraint. So the inertial range constant is that epsilon k. This is the standard Kolmogorov statement that epsilon k is independent of k. Imposing that over here means that this g that you have, the yk is what you have over here. The y is a derivative of y leads to g. G is a very comfortable thing to use because you see that E is directly expressible in terms of G. This is a quadratic in E, so quadratic in E, so you can solve for E by when you if you get the G. So G is a good thing to have. So I want to work in terms of G. So I need a flow equation for G, because then you can the E in terms of the G turns out. So I have used that, solved that quadratic equation, and what I find is that this is the result of the quadratic equation, and what it is telling you is something interesting, that it is a question of Ri times Gk, not the Richardson number alone, but it is Ri times Gk which is the decider. If that is small, then it is one type of behavior. Ek times k cubed is equal to Gk. If it is big, then it is a different behavior. Ek times k cubed is Gk divided by square root of Ri times square root of Gk. So the decider is Ri times Gk, and therefore now there is a flow equation to be determined, and just believe me that you go ahead and do it, and you are going to get a flow equation for G which looks like this. So forget everything, just trust the algebra that it has got me here. Now look at the, if I set Ri equal to 0, if Ri is equal to 0, then this 1 plus xt, and then all that I have, this x of g is just equal to unity, and this term over here becomes 1, and similarly the xg term over here becomes 1. So it is the Ri equal to 0, the Kolmogorov limit, and I should get this dg dk plus 4a equal to this. No question or no trace of Richardson number in the answer. Suppose it's very big, and now I'm going to put I have a square root of Ri over here, and if I have a square root of Ri over there, then it's you see, Ri is going to be a survivor because you have a xg which is big, and so xg cancels out with the xg in the denominator, and the xg which is going to right. Over in this term over here, xg big means that it is xt square in the top, and that is like Ri. And over here, this is a subdominant. The xt is subdominant in the denominator because it's square root, and so therefore this dominates. So the no Ri over here, but it is going to be a number different from 4. On the other hand, if I come over here, then it is xt which is square root is going to mean that it is a square root xt over here, and it is a square root Ri from here. It is a Ri to the power 3 by 8 from here, and it is a Ri from here. So it is 3 by 8 plus 4 by 8, so 7 by 8, and a Ri in this. So there is going to be a remnant Ri. So the two limits are very different. And that is what you see over here. If it is much less than 1, you see a limit which is like this, no Ri sitting there, and the solution is trivial. It is you can solve it and find that it is g of k is like a, and your ek follows as k to the power minus 5/3. And then so when is it valid? It is Ri k to the power 4/3 is less than 1. And then in the other limit, when it is Ri gk greater than 1, then there is your good old Ri sitting over here. And now once again, this is an exactly solvable equation. And you pick up gk as k to the power 8 by 5, and ek is minus k to the power, and the validity condition is Ri k to the power 8 by 5 greater than 1. So here is what is being said then, that you do an experiment, numerical or at a given Ri, and at that given Ri, if I'm looking at the small k's which are smaller than Ri to the power minus 3/4, I'll be seeing Kolmogorov-like behavior. But if I look at the larger case where it is like Ri k greater than 1 over Ri to the power 5 by 8, I should be getting into the Bolgiano. regime. So all RIs that I have, it is not obviously if I have a large RI, a Richardson number, then the range of the Bolgiano becomes very big. And if I have a vanishingly small, then the range of the, but at any RI, it is going to be a crossover, as crossovers almost of the, and now there is a question of the end of the inertial regime, which for Kolmogorov, Chandrasekhar had talked about. So if you play that game and see what is the what is the new Chandrasekhar result for so far as this particle temperature diffusion goes, you pick up a wave number which is a high wave number beyond which the energy spectrum changes from Bolgiano to minus 13 by 3. So finally then, what do I have? I have this is what I'm going to, that I focus on. I have looked at the two spectrums, Ri much smaller than 1 and Ri much greater than 1, and then the passage from one to the other and dissipative range. The results are the existence of a set of wave numbers K1, K2, K3, and if I'm below K1, I'm comfortably Kolmogorov. If I'm above K2, I'm comfortably 11 by 5. But if I go above K3, I'm headed towards the eventual exponential decay. So you see the difficulty. The difficulty is that if I take a typical Richardson number of, let's say, 10, as I said, whether 10 has any meaning or not, I don't know, but let's say 10 is a reasonable value. As the Mahendra's, that reasonable value could look like 0.01, but then you can scale prefactors and so on. But then at this 10, what are these wave numbers about? They come crowding. It's 0.18, 0.24, and 0.65. So 0.24, I mean, if I'm gone below 0.18, then I should be, so I'm restricted from 0.18, so roughly like 0.2, and I go up to 0.7. So that is not even a decade. So I'm maybe comfortable with Bolgiano only for a factor of 3 in wave number space. It is not that unless this Richardson number can be properly adjusted, and that I have a lot of difficulty in this problem with crossovers. There are scales everywhere, and the scales are never too far separated. If I try to separate it by a very big Richardson number, I'll be thrown into the two-dimensional regime. And so this is basically what the result, what I have got. So now I want to look at, I mean, is there any evidence that there is this 2015 Rosenberg doing a stably stratified fluid? Here you see is what I want you to focus on, this part over here, which is a compensated spectrum with k to the power 11 by 5. That looks reasonable, but interestingly, look at this part. This part, you see, is parallel. This line over here that you see is what the compensated spectrum would look like if you compensated it with k to the power 5 by 3. And this, as you can see, is exactly this. So what you are seeing over here, as this k goes from small values to large values, you are seeing a crossover from the 5/3 to, that is the way this particular data where there is a reasonable run of Bolgiano seems to shape up. So this is 2015, which is the only thing which I have actually found as something where you can see a crossover from one form to another. But I'll end with a crossover and this is where, what if I were to do it in coordinate space? Coordinate space, instead of K1, K2, K3, I would have R1, R2, R3. Now it is large R, Bolgiano, 6 by 5, smaller R, 2/3, which is Kolmogorov, and there would be even larger R, which is 13 by 3, or which has to the large K, where it is the intermediate R is the Bolgiano now, and you go to larger R, you are to Kolmogorov. Smaller K took you to Kolmogorov there, larger R will take you to Kolmogorov here. So it is 13 by 3 at small r, going to Bolgiano then and there. So this is what would be the outcome of what I just said for in coordinate space. And here is the last slide. And what you are supposed to see is this set of curves over here. And this is actually convective. Unfortunately, it is for a convective turbulence. So this is the only time where convective turbulence has come into the picture. And if you look at this picture over here, this is a set of 4 Richardson numbers increasing from down to up. The R values over here support a Bolgiano spectrum. So what you can't read in this region is that it is 6 by 5 over here, and almost if I measure it, I don't see 6 by 5, I see more like 1.1. But anyway, but the picture is sure they say it's more or less 1. And now you go to larger Richardson number. So larger Richardson number, the expectation was that if I have seen a Bolgiano over here, then, I mean, at larger Richardson number, I would see a Bolgiano very comfortably over here. And what the disappointing bit was that they saw a Kolmogorov over here. It is r to the power 2/3 here. It is r to the power 6 by 5 here. And that I'm claiming is exactly what you should be saying, that if I were to see r to the power 6 by 5 over here, I would look in this region where you indeed see it, and not at the very large R region, which is over here. So you see 6 by 5 over here, and you see 6 by 5 over here. Increase the Rayleigh number, the Richardson number, and you are moving to a smaller R. So that is the that is what I have come up with. In between, there is another story, that this coefficient B0, which one can calculate that. It is a small coefficient compared to the Kolmogorov coefficient, which makes life more complicated again. That means the scales are not going to favor us. And also, there is very clear-cut anisotropy. You can, the coefficient is a series in Legendre polynomials. So that's for the details of that. But over here, the message is that if I want to look for the crossover, Bolgiano is very difficult to get into because it is sort of hemmed in, and one has to probably settle for crossover. And then the point is that look for crossovers, and I have a crossover function. So that's my pitch, and that's the end of the day. So that's my story. Thanks very much. So